So now let us look at the kinematics of a particle whose position, instantaneous position, is given by this radius vector rho of t. And what we would like to do is the following. Given a rho of t, you can always decompose it along the x direction and the y direction wherever you are, like this for example, some time t, and you can write this as x which changes with time Ex plus y of t Ey. Notice that I do not put any time or coordinate dependence here for Ex and Ey because they are constants. They are constant in magnitude as well as direction once and for all. Therefore, there is no argument here for Ex and Ey, unlike what happens to x and y, because at this particular instant of time this was the x coordinate and that was the y coordinate. At a later instant of time the new x coordinate is here and the new y coordinate is there, and so on. So these are functions of time, whereas these are absolute constants. The velocity then v of t is the time derivative of this quantity, and what you need to do is to differentiate x of t with respect to dt times Ex. By the chain rule, Leibniz chain rule, you also have x of t times the derivative of Ex, but that is 0 because Ex is a constant, plus similarly dy t over dt times Ey. Once again the derivative of Ey with respect to t is 0, so you only have the derivative of y of t with respect to time. And of course this quantity is precisely what you call the x component of the velocity times Ex plus the y component of the velocity times Ey. And incidentally, if this particle is moving arbitrarily with some arbitrary acceleration, then there is no reason why the velocity should itself be constant, and therefore in general you have Vx as a function of time plus Vy as a function of time times Ey. Very often one uses a dot, overhead dot, to indicate the time derivative. So very often one uses a shorthand notation in which this is x dot and dy over dt is written as y dot, and x dot is in this case a function of time and y dot itself is a function of time. The next derivative, the second derivative, will involve a double dot there and so on. This becomes very cumbersome to use. This was Newton's original notation, putting dots for the derivative with respect to time. He called it fluxions, but as you can see the notation is rather cumbersome. It helps in the first couple of derivatives, but after that it becomes difficult. Mercifully for us in mechanics, it turns out by Newton's laws that the acceleration is what is prescribed by the external force, by whatever force you apply. So one does not generally need to go beyond the second derivative, and therefore 2 dots is something we can manage. But there are cases where you need to put more derivatives and then it is not a very good notation. I will write it as Vx and Vy in this fashion. Now what about the acceleration? A of t, this is the derivative of this quantity, so it is dVx t over dt. Ex, once again there is no derivative of this because it is a constant vector, plus dVy of t over dt times Ey. And these in general could also be functions of time. There is no reason why the acceleration should be uniform acceleration, although that is a special case. So in general this is equal to Ax of t Ex plus Ay of t Ey, and so on. So in principle the kinematics at this level in Cartesian coordinates is very straightforward, no problem at all, and therefore in this matter is simply a matter of finding Ax and Ay given the force on the object and then working back to find x of t and y of t. So much for kinematics in plane polar coordinates. There is really nothing to it at all. But if you go to polar coordinates in Cartesian coordinates, but if you go to polar coordinates, then the matter becomes more interesting and a little more intricate. What is it we are trying to do? We are trying to ask given the fact that the position of the particle is some given radius vector, some radius vector at an initial time, we are trying to find, if its path is like this, we are trying to find at every instant of time, we are trying to find what is the radial velocity, for example, or the radial acceleration, and what is the acceleration which is in the azimuthal direction. Notice it not necessarily the tangential acceleration, because that would be tangential to the path here. Here we are not saying that, we are simply saying there is an acceleration or velocity in the radial direction moving away from the origin, and then in a direction, azimuthal direction, perpendicular to the radial direction. So we have three different kinds of components. We have x and y components, Cartesian components, and then we have polar coordinates components. So this is radial and azimuthal. You could also say what is the component of the velocity along the tangent. The velocity is always along the tangent. You could also ask what is it normal to the path of the particle at any given instant of time. So you would also have, for example, normal and tangential components. We are not going to do this at the moment, since we are focusing on plane polar coordinates, but they can also be found at any instant of time. When useful, we will do so. So the immediate problem is the following: given this rho of t, what is the velocity equal to? So let us write rho of t equal to rho times, it is a function of time, times E rho, which is also a function of time, because if it is at any instant of time, it is at this point, this is E rho at that instant of time. A little later, E rho points in some other direction. So we have rho of t by definition equal to magnitude times the direction unit vector, and then the velocity v of t equal to d over dt rho of t. Now comes the interesting part. First you differentiate this, leaving that alone, and then you differentiate that, leaving this alone. So by the chain rule, it is d rho t over dt E rho of t plus rho of t d over dt E rho of t. We need to find therefore this quantity here. How does this unit vector change as a function of time? Now what is the physical meaning of this rho of t, d rho over dt? It says if the distance from the origin was this much at time t, and that is the radius vector, a little later it could have come either closer or further away from the origin or remain exactly where it is, and that is the radial velocity. So this thing here is the radial velocity, because it is the component of the velocity in the direction of the radius vector from the point. It could be positive or negative. It could be increasing, the distance could be increasing as a function of time or decreasing as a function of time. Increasing would mean this is positive instantaneously, decreasing means it is negative instantaneously, but that is the radial velocity. And in analogy with what we have here, I should really call it v subscript rho, v subscript rho of t. But now we are left with the question of finding out what is the time derivative of this quantity here. How are we going to do this? Well, for that we need to take recourse to the fact that this radius vector, the unit vector in the radial direction, E rho, we wrote it down in Cartesian components. So we had a cos phi times Ex plus sin phi times Ey. And now we have a particle moving, which means the rho and phi for this particle are changing as a function of time. So we have E rho of t equal to cos phi, which is a function of time, multiplying a constant unit vector plus sine phi as a function of time multiplying a constant unit vector in the y direction. Therefore, d over dt e rho of t is equal to the derivative of this function of time with respect to time times the same unit vector plus the derivative of this function times the same unit vector. But the derivative of phi of t, of course cos of phi of t, again it is a function of a function. You have t and then you have phi of t which is a function of t, and then you have cos phi of t which is a function of phi itself. So we know once again from the rule of calculus is that it's the derivative of this function with respect to phi. So let me write that down separately. d over dt cos phi of t equal to d over dt d over d phi cos phi multiplied by d phi over dt by the chain rule once again, but this is equal to minus sine phi because the derivative of the cosine is minus sine phi multiplied by d phi over dt. If I use that here, this becomes minus sine phi times d phi over dt times Ex. So let us write it with the d phi over dt coming out. So this is equal to d phi over dt, and that is a function of time, times the derivative of this function with respect to phi which is minus sine phi, the derivative of this function with respect to phi which is plus cos phi. So now this becomes minus sine phi times Ex plus cos phi times Ey. But if you recall what we had said about the vector that is normal to this E rho, the unit vector in the azimuthal direction, if you recall the formula for that, it was precisely minus sine phi times Ex plus cos phi times Ey. And that is exactly the combination here. So we have a very useful formula which says d over dt of the unit vector in the radial direction as a function of time in general is equal to this quantity here, and that is E phi. So we have d phi over dt times E phi, which is of course a function of time out here in this fashion. A very useful formula indeed. In fact, while we are at it, we may as well find out what is the derivative of this function with respect to time. So let us also write d over dt E phi of t equal to the same thing as before. We differentiate this with respect to time, since phi is a function of time. The derivative of sine phi is cos phi, there is a minus sign here, and then the derivative of phi itself. So this is going to become minus cos phi d phi over dt times Ex. So this is minus cos phi d phi over dt Ex, and then this term here, the derivative of cos phi is minus sine phi. So there is a minus sine phi and then a d phi over dt to differentiate this function here times Ey. But that is equal to a minus sign outside, d phi over dt outside, and then inside the bracket you have cos phi times Ex plus sine phi times Ey. We go back to this equation and realize that that combination in the square bracket is just E sub rho. So we have the complement of this formula which says this is equal to a minus d phi over dt of t times E rho of t. So to sum up, the rate of change of the radial vector, unit vector in the radial direction is along, is a unit vector, there is a unit vector here along the azimuthal direction. The rate of change of the azimuthal unit vector is along the radial direction here with appropriate signs here, and this quantity d phi over dt could be positive or negative. Whatever it is, it multiplies these unit vectors. So the whole point is the rate of change of this vector, unit vector, is along the other unit vector, and the rate of change of the other unit vector is along the first unit vector, where these two unit vectors form a basis for all points in the plane here. So once we have that in place, we can now write down these formulas properly. This therefore becomes V of t is equal to, this quantity here is d rho of t over dt times E rho of t here, and then for E rho of t, d over dt E rho of t, I need to substitute this. So there is a term here which is plus rho of t d phi over dt multiplied by E phi of t. So just as the original rho of t had only a radial component, E rho of t times rho, the velocity now has, however, both a radial component as well as an azimuthal component. So this is the radial velocity and this is the azimuthal velocity. Okay. But we can do a little more physical identification here. You can see that what is really happening is that if I call this V sub rho, it says V of t equal to, let us put dots to tell us where the time derivatives are going in. So there is a rho dot as a function of time, of course, and then E rho of t plus rho of t phi dot of t E phi of t. And this quantity here is what I call the radial velocity. Strictly speaking, I should multiply it by the unit vector, then call it the radial velocity. But you know this loose terminology, very often when I resolve a vector into components, even without the unit vector I still call it a component, whereas a vector must be a sum of vectors, can't be a sum of addition. What I am saying is, if I write rho equal to x Ex plus y Ey, strictly speaking I should call this the x component and this the y component of the vector, because component means part, but in loose language I often say x is the x component, y is the vertical component of the vector. So in the same sense, one often calls this the radial velocity, it is actually the radial speed, if you like. So this is the radial part. It comes whenever the distance from the origin changes as a function of time. If it does not, if it is moving in a circle, that part would be 0 identically. And this part you can now identify what is happening. This quantity here is obviously the angular velocity, because angular speed, because this thing here tells you how the angle, the azimuthal angle changes as a function of time. So this is the angular speed, and let us be technically correct, this is the radial speed. Now we should check physical dimensions all the time. The distance, of course, or the displacement has got dimensions of length, physical dimensions of length. Velocity has physical dimensions Lt inverse in this fashion, and we must make sure that is happening everywhere. This rho has dimensions of length and rho dot has dimensions of Lt inverse. So that is okay, this part is okay. That is a unit vector. It may change its direction with respect to time, but it does not matter. It is still a unit vector and is dimensionless, no dimensions at all. So this part is all right, it has got dimensions of velocity. What about this? Well, this has dimensions of length. And what about the dimensions of angular velocity, angular speed? Well, angle has no dimension at all. It is measured as arc divided by radius, as you know, it is a dimensionless quantity, but there is a dot sitting there. So there is a 1 over t sitting here, and therefore this has dimensions, phi dot has dimensions t inverse, and again as before E phi of t has no dimensions at all, it is a unit vector, and therefore is a dimensionless quantity. Okay. So we are okay dimensionally. The velocity now has been decomposed into a radial part and an azimuthal part in this fashion, starting with the fact that the position itself had only a radial part. So we started with that, and we have derived this fundamental relation here, which tells you that the velocity would in general have two components, one because the distance from the origin is increasing or decreasing, and the other because the azimuthal angle in the path is changing, of a point on the path is changing, and these are the two components. This is the analog of the Cartesian quantity we wrote down. We wrote V of t is Vx times Ex plus Vy times Ey. Now we got slightly more complicated quantities. There is an angular speed coming in, there is a radial speed coming in, and so on. Well, at the next stage, and we do need to go to the next stage because, as you know, Newton's law is going to prescribe the force which will control the acceleration. So we need a formula for the acceleration. The next thing we have to do is to find A of t equal to dv over dt. And what is this going to be equal to? Well, again I use the chain rule, and if I differentiate this, which is already d rho over dt, I am going to get d2 rho over dt2, which is rho double dot of t, and then this part remains unchanged. So that is the derivative of this term times that by the Leibniz chain rule, and then there is a rho dot times the derivative of that. So this is rho dot of t times d over dt of E rho of t, that is the next term, plus I need to differentiate this. So there is a d rho over dt in this fashion, and the rest of it remains unchanged, phi dot of t E phi of t, plus again by the chain rule there is a rho of t, I differentiate this, that gives me a phi double dot of t E phi of t, and finally there is one more term which is rho of t phi dot of t d E phi of t over dt. So you really have a large number of terms. You differentiate this, you get 2 terms, you differentiate this, you get 3 terms, and therefore you have 5 terms in all. And we have to add up all these terms here. Well, let us do that. Our target again is to realize, is to see that, is to exploit the fact that finally the acceleration, again being a vector in the plane, should be decomposable into a portion which is proportional to E sub rho of t and another portion which is proportional to E sub phi of t. So we need to find out what is the radial component and what is the azimuthal component for the acceleration, and that is where we are headed for. So we have A of t equal to the first term is rho double dot of t E rho of t, and you will recognize what this term physical meaning is very simply, because just as this portion of it was the radial speed, this part is the radial acceleration, if any. That is the first term, that part is taken care of, plus rho dot of t, and then let us find out what this quantity is, but we already have a formula for that. That says d over dt E rho of t is phi dot times E phi of t, so phi dot of t E phi of t just to reduce the notation a little bit, I have called d phi over dt phi dot out there. So that takes care of this term and this term, and then we have a rho dot phi dot e phi of t. So we need to put that in, rho dot phi dot e phi of t, it is the same as this term, so you really have twice that, and that has taken care of this third term. And the fourth term is rho times phi double dot e phi of t, we have to leave it as it is, plus rho of t phi double dot of t e phi of t. You have no choice in the matter, this is gone, and finally you have rho phi dot d phi over dt, which is equal to phi dot times e rho. So there is a minus sign there and there is a phi dot appearing once again, so this is equal to plus rho of t, first part, and then phi dot squared of t. So you differentiate and then you square it, so it is phi dot squared of t times e rho of t. We must check dimensions once again. This has dimensions, physical dimensions of L t to the minus 2 because it is an acceleration. This has dimension L t to the minus 2 from here, so that is okay. This is L t inverse, so that is okay. This is L t to the minus 2, that is dimensional, that is okay. This is L, this is dimensionless, and then there is a dot squared, so that is t to the minus 2, and that is okay too. So we are dimensionally all right, and all we need to do finally is therefore is to collect portions proportional to e rho and collect portions proportional to e phi, and you discover that this we need a minus sign somewhere. The last term was rho of t phi dot of t de phi over dt, but that de phi over dt had a minus sign, so this is a minus sign. Yeah. So this says rho double dot of t minus rho of t phi dot squared of t in this fashion, that multiplies e sub rho of t. So it takes care of this term and this term, and then we have terms which look like plus rho of t phi double dot of t, that takes care of this term, plus twice rho dot of t phi dot of t multiplying e phi of t. So that is our grand finale, that is our final formula for the general acceleration in a plane in plane polar coordinates. A radial portion and an azimuthal portion. Surprisingly, the radial portion, unlike the velocity, which just had a radial speed out here, and this was rho times the angular speed if you like, in the acceleration some new terms have appeared precisely because these unit vectors change with time. So what has happened is that there is a radial acceleration which has appeared here, but there is an extra term which has appeared here which depends on the square of the angular speed out here multiplied by a radius vector. Similarly, in the case of the azimuthal component, you have got this for dimensional reasons times an angular acceleration because it is the second derivative of the change of the azimuthal angle. The first derivative is the angular speed, and this is the rate of change of the angular speed. So it is the angular acceleration, just as this is the radial acceleration, but there is an extra contribution which is dependent on a combination of both the radial speed as well as the angular speed out here. So you have this extra term here, and it has emerged completely naturally simply by differentiating these unit vectors carefully. But these terms will turn out to have physical significance. This is the most general formula that you can have for the acceleration for a particle moving in a plane. Everything is already here in here, There could be cases depending on the special motion. For instance, if the particle is moving on a circle, then the distance from the origin is fixed, then rho therefore is constant. This becomes the radius of the path. This is identically 0, this term is then identically 0, does not change at all. On the other hand, once you have a variable rho, these terms are non-zero and they exist, you can't help it. So that is exactly what this kinematics does. It gives you all possible terms, then says in special cases things may reduce, may become simpler. Later on we will see that this term here is related to what is called the centrifugal acceleration in a rotating frame, and this term here is related to what is called the Coriolis acceleration. So these terms are actually related to what are called non-inertial forces in a suitable context, and we will talk about that when we get to it. But I want you to appreciate right away that this general formula arises from using no more than very simple vector analysis and using the chain rule for differentiation of functions of time, and that is all that has been done, and all these things have already popped out automatically, and this is in a plane already. The moment you go to the third dimension, things can get a little more complicated, but this already begins to tell you that when you write these problems down in coordinates other than Cartesian coordinates, then various physical effects can be seen to emerge directly, and we will see how this plays a role when we analyze motion, for instance non-uniform circular motion in a plane and so on. If you have uniform circular motion, then the angular speed is also a constant, and this term vanishes identically, and this is replaced by some omega squared, where omega is a constant uniform angular speed. So all special cases can be read out from this, but this is the general formula here. Of course you can go on to differentiate it once more, get an even more complicated formula, but like I said, when we do dynamics, because of Newton's laws saying that the force will prescribe the acceleration, you need not go beyond this in general. So much for kinematics in a plane, and the next thing we need to do is to go on to three-dimensional motion. But first we need to talk about vectors in 3 dimensions, and then we introduce other coordinate systems.